Hello Year 12, welcome back to my next lesson on chapter 11. I'm going to be looking at section 11.5 today, which is proving and using the constant acceleration formula. Right, just a reminder from what we've already done in the last two lessons. To get from displacement to velocity and velocity acceleration, we differentiate, and going the opposite way, we integrate. That's key, fundamental to this chapter 11. Make sure you learn that and know that. Okay, what we're going to do today is we are going to prove a couple of the formulas, the kinematic formulas, which you may be asked to do in the lesson. Now, in the exam. So I'm going to actually go through this example 8. So that's, I know Pete Hart in his videos, he goes through the examples. I'm going to go through this one here. Then I'm going to go through 2 of the harder questions from 11E. I'm going to go through question 5 and question 6 from 11E. And I'm going to set you questions 1 to 4 to have a go at doing. So let's go through the example in the book. Right, you've got a particle, it moves in a straight line with constant acceleration. Okay, so this is constant acceleration, this lesson. We start off with initial velocity u and initial displacement s. So when we mean initial, this is when t equals 0. We want to prove this formula here. So how can I go about proving this formulae? Well, I know that to get v, I can get v by integrating acceleration with respect to time. So if I integrate this, I get at plus my constant of integration. Now, to find c, let's go back to my initial conditions. At time t equals 0, my velocity is u. So let's put that in. We get u equals 0 plus c. So we can see c is 0. Let's put that back into this equation. V equals at plus u. Hence we've proved that equation. Okay, so that wasn't too hard. Let's look at another equation that we can now prove. So this time we're going to look at this equation. This is part B, this kinematic equation here, where A is constant acceleration. Okay, well, we know to get displacement, we can get displacement by integrating velocity. And we know, if we look at what we proved in part A, if I put in this equation here, u plus at, if I put that in for velocity and integrate it with respect to time. So let's do that. So I get ut plus a, remember a is just constant, t squared over 2 plus my c. Remember u also is a constant number, so that's why we can do this integration. T is my variable, t is what's changing. Okay, let's find c. So we can find c at the beginning, at time t equals 0, we're told the displacement is 0. So if I put that into here, I'll find that c is 0. So hence I get my equation that I needed to prove. You might be asking, why couldn't I just integrate v at the beginning? Well, v actually is a variable. I can't just say this is v t plus c, because v is changing. However, u and a are constants. Right, so let's now look at one of the harder questions from exercise 11E. So I'm going to look at question 5. Question 5 on page 192. A particle moves in a straight line with constant acceleration. The initial velocity of the particle is 5, and after 2 seconds it's moving with velocity 13. Find the acceleration of the particle. It says, watch out, an exam question might specify that you cannot use certain formulae or techniques. In this case, you need to use calculus, i.e. differentiation or integration, to find the answer in part B. Okay, find the acceleration of the particle. So, we know that it says in the question it's moving with constant acceleration, so we can use our kinematic formulae. So I'm going to look at Suvat and think, what have I got? Okay, well, I have got, if I look at this condition here, I know at time 2 seconds, I know my velocity is 13. I want to find A, and I know my initial velocity is 5. So I think to myself, which equation connects all of these? Well, the equation that connects all of those is V equals U plus AT, the equation that doesn't involve S. Okay, so I want to find my acceleration. Let's sub in what I do know. V is 13, U is 5, A I'm trying to find, T is 2. So let's just solve that. 13 take away 5 is 8. So we can see A is 4 meters per second squared. And that's constant, it doesn't change. Okay, next question, part B. Without using Suvat, okay, so we've got to use calculus, show this equation here, where P, Q and R are constants that we want to find. Okay, so I have got my velocity. I know I want to find here displacement. Okay, now I know this equation. I know velocity is the integration of acceleration. I know my acceleration is 4. So I know if I integrate this, I will get my velocity. So can I find my velocity? Can I find my constant of integration? So if I go back to the beginning with my conditions at the start, I know that when U is 5, T is 0. Okay, so I'm going to say V is 5 when T is 0. Let's put that in here. And I will get my constant of integration to be 5. So now I have a formula for velocity. However, I don't want to find velocity. The question asks to find displacement. So I need to now know I need to integrate again to get my formula for displacement. Okay, just move that up so you can see it on the video. So let's integrate again. Add 1 to the power, divide by the power, and don't forget my constant of integration. Okay, each time I integrate, this constant of integration will be a different value. So really, maybe I could use different constants here to show that they are different numbers. So let's do that. Let's put in the conditions that I know. I know at the beginning, if I go back at the beginning, okay, I know that, well, it hasn't travelled anywhere at time 0. So I know when t equals 0, s equals 0. So let's put that in here. So I can see my constant's going to be 0. So let's just tidy this up and I get this equation for my displacement. Okay, so let's compare that to what the equation was asked for to find. This is what you were asked to find. So we can see that P must equal 2, comparing those two, and Q must equal 5. P equals 2, Q equals 5, and there is no constant for R. So that is the end of that question, question 5. Okay, look back at that video again. If you need to clarify any points, email me if that doesn't make sense. But I'm going to go through one more question now. Question 6. The toughest question, quite a lot of problem solving in here. If you want to have a little pause now, have a break, grab a coffee, please do that. I shall have a sip cup of mine. Excuse me. Great. Okay guys, let's look at question 6. So, a train travels along a straight track passing point A at time 0. I've done a little diagram for this. And passing point B 40 seconds later. I always think in diagrams, as you know. Its distance from A at time t seconds is given by this formula here. Okay, and t only goes between 0 and 40. Right, the first question says, find the distance AB. Now, is it saying here that it's moving with constant acceleration? It doesn't. It says for part B, show that the train travels at constant acceleration, but we can't assume that for part A. Okay, so how are we going to find this distance AB? Right, well, we've got an equation connecting to find the displacement S. We know at B, it's at 40 seconds. It takes 40 seconds to get to B. So if I just put 40 seconds into my formula, that will get me my solution for the displacement. So what I mean is, we're just going to say 25 times 40 minus 0.2 times 40 squared. And if I work all of that out, you should get 680 meters. Again, you might want to have a go at this question before I do it, and then just check your solutions with my video. Okay, next, show that the train moves with constant acceleration. So we need to show that A is just a number and does not change. So I know to get acceleration, I have to differentiate velocity, and to get velocity I have to differentiate displacement, going back from here. So I'm given displacement. If I differentiate once I get velocity, if I differentiate twice I get acceleration. So let's do that. So velocity is displacement differentiated. Okay, so I know that my displacement formula is this. So if I differentiate it, okay, not integrate, so here, bring the power down, take 1 off the power, so t to the 0 is just 1. Bring the power down and take 1 off the power. No constant of integration. Okay, and I know if I differentiate again, if I differentiate velocity, I'll get acceleration. So let's differentiate this again to get acceleration. 25 will differentiate to nothing, and this will just differentiate to 0.5. I'm differentiating this with respect to time. So I've just got a number, hence the acceleration must be constant. It's always that, independent of what the value of t is. Okay, we can see that it's got negative acceleration, so therefore it must be accelerating the other way. Okay, that was part B, showing it's got constant acceleration, i.e. the train's decelerating and it's slowing down. Right, next one, C. So C says, again, this is going to get quite complicated now, so bear with me. A bird passes point B, so I've got my bird here, okay, at time t equals 0. So we're going to start timing the bird at this point here. Its initial velocity towards A, so this is going the opposite direction, so we have to be careful with our signs here. So it's travelling this way, so my initial velocity is 7, but my positive direction, I'm going to use this as my positive direction. So I should put here -7 for my velocity going this way. So I'm just going to write that again. U is -7. It flies in a straight line towards A with constant acceleration A of 0.6. Now it's moving this way with acceleration, so I'm going to say the acceleration is -0.6 because it's in the opposite direction to my positive direction. So that's where you may go wrong on this question. Find the distance from A at which the bird is directly above the train. So we've got a situation where my train is travelling this way, my bird is travelling this way, and say this is where my train is here, and we want to know when my bird is directly above the train. Okay, and we want to find the distance from A. Okay, so the bird is starting at B, travelling this way, the train is travelling from A this way. So that's the scenario we've got. We've got a picture there to represent our scenario. So if we look, we need to find when the distance is the same for the train and the bird. Now, what information do I have? So let's just look at the conditions we have for the bird. So the distance of the bird from A, well, we know this distance is 680. We looked at that in part A of this question. We know the initial velocity of the bird is -7 because it's flying this way. We know this is at time equals 0, and we know the acceleration of the bird is -0.6 because it's going this way. Right, now we want to find when the distance of the train and the bird is the same. That's what we're trying to find, that the distance from A of the train and the bird is identical. So we want to find the distance of the bird. We know the distance of the train. We know the distance of the train. We've got a formula for that here. This is the formula for the distance of the train at different times. Right, so how can we find displacement? Well, we have the acceleration. So first of all, if we integrate the acceleration of the bird, we will get velocity. And if we integrate that again, we'll get displacement. So we know that the acceleration is constant. If we integrate that, we get this plus our constant. Okay, let's put in our conditions for velocity at time t equals 0. At t equals 0, my velocity is -7. So when t is 0, velocity is -7. So this is my constant of integration. So my formula for velocity of the bird will be negative 0.6t take away 7. Now I want to integrate this to find my displacement. So I'm going to integrate velocity now to find displacement. Okay, so let's do that. I'm going to add 1 to the power divided by the new power plus another constant of integration. Okay, let's put my conditions in to find my distance s. Well, we know that the distance of the bird at the beginning is 680, that's at time 0, so my constant of integration is 680. So my final, if I just tidy up this equation now, this is my equation for the distance, the displacement of the bird from point A. So I've got now 2 conditions. I've got 2 formulae. I've got this one for the train. I've got this one for the bird. So if I put them equal to each other and solve, then I can find the time when they are both have equal distance. So let's put them equal to each other. So I've got this equation here equals this equation. Okay, and if I just tidy all of that up, take it all to one side, multiply everything through by 10, I will get this equation here. So take it all to one side, multiply by 10, and I'll get this equation. Luckily, I know it's a horrible equation, but luckily it does factorise to minus 20 and 340. So t is 20. I can't have negative time, so I ignore this part, this answer here. So at 20 seconds after the start, the bird is directly above the train. The question asks to find the displacement. We can put it into either of the equations, the train or the bird equation for displacement, and for each case I will get the same answer as 420 meters. So if we go back to my picture at the beginning, this is the 420 meters at time 20 seconds that the bird is directly above the train. But you won't get much harder than that, year 12. Well done for sticking to that problem. And what I'd like you to do, and I have gone through the harder ones, so don't worry too much. You're going to have a go now at exercise 11E, questions 1, 2, 3 and 4, and submit that to your teacher, please. And then we have finished chapter 11. My next lesson will be going through some harder questions from the mixed exercise and possibly some exam questions as well. So we'll have a couple of lessons, I think, on revising chapter 11, and then we'll give you some questions to do with a little assessment. Okay, hope you enjoyed watching. Thumbs up, stay safe, get lots of exercise, try and stay happy. Bye! We know that V equals or if we integrate acceleration, we get velocity. So we know this. If we integrate acceleration with respect to time, we get velocity. So let's integrate this. V equals AT, remember A's constant, plus my constant of integration C. Okay, well let's find the constant of integration. How are we going to find that? Well, we know the condition here at the beginning, S is naught and t and velocity is equal to u. So at the beginning, when t equals naught, my velocity is equal to u. So let's put that into this formula. U equals a times 0 plus c. So u just becomes c. So let's substitute that into our formula. V equals at plus u. Or just rearrange that, v equals u plus at. And hence we've got our equation that we need. Okay, the next equation you might be asked to prove is this one. So how are we going to get that? Well, the other one we got from integrating acceleration. So in this case, to get displacement, we have to integrate. What do you know? Well done. Okay, so to get S, we have to integrate velocity with respect to time. So let's do that. We're going to get S equals vt plus our constant of integration. Now, I know from before that v is equal to u plus at times t plus c. Yeah, so all I've done here is I've replaced the v with what I got proved before, u plus at. So if I multiply that out, I am going to get ut plus at squared plus c. Now I need to find my c, and I know at the beginning when s is naught and t is naught, u is naught. So when s equals naught,